Hello, thank you so much for tuning into my YouTube channel. In this video, I want to talk about whether or not we could get to spectral reflectance data from color data. Let's get started. So we want to talk about if we could get to spectral data from color. Spectral data and the corresponding color data are related to each other. In other words, having one of them available could result in the other, at least in terms of mathematics. If you look at these curves, you see that the yellow butter and the red tomato and the green lettuce, their spectral characteristic are also showing that, like the bump in the middle wavelengths in the lettuce would show us that this is green color, or the red characteristic in tomato. So they are very much related to each other. Let's talk about the color spaces. Color of an object could be quantified with quite a few color metrics, the most prominent of which is RGB values of a digital camera, or even the new monitors. They also work with RGB color space. There are other more standard color spaces such as CIEXYZ, CLAB, and sRGB, which is also RGB. sRGB is a standard version of RGB. All the color space values in these color spaces consist of three variables. In the case of RGB, they are the values of red, green, and blue primaries, the combination of which leads to the color of the object as we know. As shown here, like this is an object, and the combination of RGB primary would lead us to the color. And it is important to know that any two objects, or even more of any type, could lead to the same color. In other words, the same values for RGB primaries. In other words, we have two materials that are not the same type, but in a specific viewing condition, in this case, the light source, under a specific light source, the colors match. In other words, they would lead to the same combination of RGB. But as soon as the viewing condition changes, and in this case again the light source, the color is not the same anymore. So having the color values are not as reliable if we want to identify the material, because two types of material here under a specific viewing condition, they have led to the same color combination in RGB color space. Okay, let's talk about reflectance spectra. Reflectance spectra, on the other hand, is the fingerprint of objects using which the object could be identified. No object of the same type could have a matching spectral reflectance. Even though the colors could be the same, the reflectance spectra could be not the same. This is called metamerism in the field of color science. As you can see here, we have two spectral reflectance that are not the same. Obviously, they're not the same, but under a specific viewing condition, they have led to the same appearance. The color is the same. But as soon as we change the viewing condition, we use another light source, the colors do not match anymore. So that's called metamerism in the field of color science, but also it shows how reliable spectral reflectance is as opposed to color in identifying what objects we're looking at. But what is the relationship that spectral reflectance and color have? Going to color from reflectance data is very easy, but can we also go to spectral reflectance from color? Let's quickly explain how we can go from spectral reflectance data to color. All we have to do is to just do this very simple multiplication and then sum them up over the visible spectrum, where S is the spectra of the light source, and R is the reflectance spectra of the object, and RGB here are the sensitivity of the standard observer watching that particular object. And then we just sum them up over the visible spectrum. Very straightforward. S is actually the spectral This the spectra of the is the spectra of the light source as we have shown here, which is also called spectral uh, mm, distribution of the light source. So very straightforward, but can we also do the same thing when we want to go from color to a spectral reflectance? No, going from color to a spectral reflectance is a matter that is way more complicated. You see, the same color could end up with quite a few spectral reflectance curves. For example, imagine we have an object whose color is this beautiful green. We have no idea what the object is, but all we know that the color is green. So what can we say about the object? I mean, it could be a leaf with the same color, or it could be a paint on a beautiful piece of work of art, or it could be anything else. So this leads to the spectral reflectance to have a lot of possibilities. Which one is it? We have no idea. We just know the color. Also, the problem here is we have more unknown variables than the known ones. In other words, our problem is of ill-posed nature. What does it mean? That means there are more than one answer to our unknown variable. If, for example, we have three color variables, we call them RGB, we have at least 31 unknown variables, which are the values of the spectral reflectance at each wavelength. Of course, across the visible spectrum from 400 to 700 at 10 nanometer interval. But how can we solve this problem then? Just very quickly, we see that we have color here, which has three variables, but this is the visible spectrum here, which has at least 31 unknowns. So how can we go from 3 knowns to 31 unknowns? There have been a lot of solutions offered to solve this issue and go to the spectral data from color data. We are not gonna go through those methods in this video. These are the methods that have been famously applied to this issue. But we just wanna touch on how they all generally work. Just the general solution to this problem, I think, would be a good start. So overall, the way these methods work is they first come up with a training data set for which they have both spectral and color data. And then they use a system to train using this data that they have. The system learns to go from color data to the spectral data using the training samples that they have available. After that, the system would be ready to estimate the spectral reflectance of any color that is input to it. In other words, the testing samples that they're going to apply to the trained system. Then we would be able to estimate that the testing samples spectral reflectance from their color. But there are some notes to pay attention to. It is very important to pay attention to the type of the material that are used for training and test. The type of the material used should be the same. In other words, you cannot use a different material to train the system and then use another type of material as a test to estimate the spectral reflectance. For example, if I use Macbeth color checker to train my system, I cannot use that system to estimate the spectral reflectance of a leaf, because the type of the material in Macbeth color checker is not the same as leaf. So this would not lead to an accurate result. It goes without saying that if I want to come up with an ideal system which could estimate the spectral reflectance of all the objects in the world, we have to have the reflectance spectra of all the material types that exist on the planet Earth to train the system. This is the general system that we could come up with when it comes to spectral reflectance estimation. So in conclusion, we could say that going to spectral reflectance from color is possible, and but there's also some notes we have to pay attention to. We have to be cautious with the type of the material that we are going to use to train the system, and also it's still a challenge to reach a general solution. And in one of the next videos, I will speak about the methods that have been devised to tackle the problem of spectral reflectance reconstruction, as they refer to, from color. And it should be noted that this is only applicable to the spectral reflectance in the visible part of the electromagnetic spectrum, and we can't just go use the color and estimate the IR or UV part, because the standard observer that is watching that, he can't see UV and IR to start with, because it's because this problem is like some sort of compression problem, but the compression that has been caused by the observer. So this is only applicable to visible spectrum. Thank you so much for watching this video. I hope you liked it. If you liked it, share the videos with your friends and also subscribe to my channel. Thank you. Have a good day.